This is what modern AI agent development often looks like: a swarm of unmanaged processes constantly pulling at your codebase, getting in each other's way. You end up with what developers are calling a mass psychosis problem. Do you deploy 15 autonomous agents and hope they figure it out? Or do you step in and manually review every single line of code they produce? The solution to this chaos is not writing larger prompts, nor is it relying on black box frameworks to do the thinking for you. A reliable AI system requires rigid architecture. To achieve that reliability, you take a prototype into a production-ready state through a strict 4-level architectural maturity model. To stop building sloppy, unpredictable systems, you have to transition your mindset from a synchronous coder to an asynchronous engineering manager. Level 1 is the starting line. This is where you utilize standard agent frameworks like LangChain or Llama Index. If your goal is simply finding product-market fit, these tools are highly effective. You can deploy a functional prototype in under 30 minutes and prove your concept works. This diagram illustrates the limitation of frameworks. They function as opaque systems. An input goes in, an output comes out, and the internal execution steps remain completely hidden from the developer. That black box nature quickly becomes a liability. When you try to build a serious production application, you cannot open that box to customize the modularity of the system. A framework proves your idea is viable, but its rigid boundaries prevent you from applying the precise control required to scale that concept into an enterprise-grade product. To gain true control, you advance to level 2. Here, you abandon the framework and build the agent manually as a deterministic state machine. Stripped to its core, every reliable AI agent is a basic recursive while loop connecting predictable nodes. We can track the cycle. The system receives a user task, triggers a tool action, runs a completion tool, and exits at task complete. Once you have this structure, you encounter the second rule of level 2, avoiding prompt bloat. There is a persistent fallacy that complex tasks require massive system prompts. As this visualization shows, giving a frontier model too many edge case instructions and complex if-else logic degrades its performance by causing sensory overload. Frontier models perform exceptionally well when you provide leaner, more direct instructions. By stripping away bloated prompt logic and locking the agent into a rigid, transparent loop, you drastically increase the predictability and success rate of the model. Rule 3 of Level 2 introduces a pseudo-RL testing pipeline using a command line interface. You build the agent so that other AI coding agents can easily interact with it via a continuous integration pipeline, allowing them to autonomously test, iterate, and modify the code. Rule 4 demands that human engineers dictate the high-level architecture. You never let a model determine the foundational state machine design. The final rule of Level 2 requires mastering API asymmetry, specifically regarding the reasoning traces generated by models like Opus and Gemini Pro. Look at this API compute loop.
During test time compute, the API generates specific cache data, isolated reasoning traces nested inside the return payload. You must perfectly reformat them into an exact structural match before sending them back, or the API silently degrades the response quality. Ignoring the exact formatting requirements of API reasoning traces means you are artificially capping the performance of the most advanced models on the market. Once your architecture is sound, you reach Level 3, which addresses the primary temporal constraint. Complex agentic tasks require 8 to 10 minutes of test time compute. Because of this wait, your system is inference-bound. You cannot afford to wait synchronously for a single agent to finish its execution before starting the next task. To maintain high throughput, you must deploy multiple agents mutating the same source code simultaneously. This UI shows the optimal form factor for isolating states and managing parallel execution, a Kanban board, clearly dividing the workload. This interface turns you into an engineering manager. Instead of reading individual lines of code, you visually track which state machine loop each agent is currently executing. When an agent hits an ambiguity or needs approval, it automatically transitions its own card into the review column, waiting for your input. The Kanban layout serves as the essential interface required to prevent code collisions when orchestrating a fleet of autonomous, long-running state machines. The final bottleneck in this system is relying on your local machine to handle dependencies, UI testing, and environment setups. This sequence of server racks lighting up represents a massive parallel cloud infrastructure spinning up to handle heady asynchronous workloads. This is level 4, migrating your Kanban-managed agents completely to the cloud. A cloud agent can execute a 60-minute automated task like manually clicking through a GUI without freezing your laptop's resources. Deploy complex tasks from your phone, let cloud machines iterate headlessly, and review the final pull request. True engineering scale is achieved only when execution environments are decoupled from local hardware, allowing fleets of agents to iterate continuously in the background. The architectural journey moves linearly, starting at a black box framework, manually building a recursive state machine, managing parallel execution via Kanban, and parallelizing it in the cloud. A disciplined system architecture combined with strict API handling will consistently outperform massive prompts and complex internal routing. As this pristine factory floor illustrates, the final state of disciplined agentic engineering operates completely smoothly and predictably. Escaping the chaos of AI slop requires a shift in perspective.
You must stop treating models like humans who need verbose instructions and start treating them like raw compute engines requiring rigid, deterministic pipelines. To put this into practice, explore our technical tutorials and expand your engineering toolkit on Learn by Doing with Stephen. And for deep dive audio discussions regarding data and AI architecture, listen to Stephen Data Talk on major podcast platforms.